Good morning and welcome to the third day of the Bioconductor 2024 conference. It's my pleasure to introduce Dr. Sandra Safo, who is the McKnight Land Grant Professor at the University of Minnesota. I was pleased to review Dr. Safo's CV and see that she has received the Emerging Leader Award of the Committee of Presidents of Statistical Societies, the COPS, NIH Outstanding Investigator 2021 to 2026. And she has a very nice app which will introduce us to Multiview learning, and recently has worked on machine learning in the domain of irritable bowel disorder. So with no further ado, I'd like to welcome Dr. Safo to the podium, and we will have a talk on supervised multiview learning. Thank you.
Thank you so much. It's quite early in the morning, so I appreciate that you're all here today to listen to some of our work on data integration. So I'm using the word multi-view learning, but then it's also data fusion, data integration. So don't get, I don't want any misunderstanding here. It's just the same concept. So I will be talking about some of our methods that we have developed for data integration. So we've had a lot of talk about single cell, spatial transcriptomics, genetics, genomics. But beyond that, we also, for the same person, we are collecting gene expression, proteomics, metabolomics data, and we could also have electronic health records data, social determinants of health, that will measure the lived experiences of individuals. So then a key question becomes how to put all of these different data types together rigorously to understand complex disease mechanisms, perhaps for disease prediction, and if you are interested in clustering for disease subtyping and endotyping, with a goal of providing greater insight into disease mechanisms. So I'm going to focus on some of the methods that we have developed for biomarker identification or disease prediction. But then integrating data, all of these data from different sources is modeled with some challenges, and that could be due to the complexity of the data, the heterogeneity in the data, and the high dimensional nature of the data. So by data complexity, thinking about the assumptions that drive the underlying data. So each data type will have its own data distribution. There is a complex interactions within a particular data and even among different data types. And so nonlinear methods become important for unraveling the complex relationships in these data types. And also using prior biological knowledge about how the data set, how the variables are related become useful. For heterogeneity, the data itself could be heterogeneous, and also the disease that one is studying could be heterogeneous. So by data heterogeneity, I can think of the different platform and technology that are used to generate the type of data. If we think about metabolomics, for instance, we can obtain metabolomics data from mass spec. We could also get it from Biocritis, and then we have different platform giving that same type of data. And so then normalization becomes important and batch correction becomes relevant. Then for high dimensional data, I'm thinking about a lot more variables than there are samples. So we could have thousands and tens of thousands of variables compared to the samples. And nowadays, some databases, we are also having a lot of samples and a lot of variables. And so dimension reduction becomes important. So how do we reduce these high dimensional data to a form such that it is interpretable without losing a lot of information? Variable selection becomes relevant. So if you think about having a lot of variables, then the assumption is that not all the variables are important in driving the disease and the relationship or the variation we are seeing in the disease. So then variable selection is important and scalable methods are useful. So a popular research question in multi-omics studies. So remember I said, when we integrate all of these different data sets, it could help us understand complex disease mechanisms. One common question for multi-omics studies is to understand molecular signatures or elucidate molecular signatures that are associated with a particular clinical outcome or that discriminate between those with and without a particular condition based on multi-omics, and if you have phenotypic, based on multi-omics and phenotypic data. So this is a key question that we are normally asked or one tries to answer when we're looking at multi-omics studies. So if I gave you that particular question and we had these different types of data, then when I think about the approach, the one-size-fits-all method will assume that we're looking at all data, all individuals, agnostic to any subgroups, subgroup heterogeneity. And so, for instance, if we have genetic or genomic data, proteomic data, we profile and we use integration method, analyze the data, and we select relevant genes and relevant, let's say, proteins that discriminate between the disease condition or that predict or associated with a particular outcome. So that is what I am referring to as one-size-fits-all methods. And there are different approaches for carrying out this particular analysis. I'll focus on one approach in this particular talk. When I think about bespoke methods or methods that are a little bit tailored to help understand the disease heterogeneity, I'm thinking about a scenario where there is heterogeneity in subgroups. So for instance, for a particular disease, there might be genetic differences or there might be some epidemiologic difference between males and females. So males may present differently, females may present differently. And the subgroup is not just for males or females. It could be different, it could be race, it could be social determinants of health, or it could even be disease subtypes, so cancer subtypes. And so can we find genes, can we find, let's say, proteins that are common between the subgroups that we are considering and that are specific to a particular subgroup? So then the goal here becomes highlighting the commonalities and also the differences in the subtypes. And that becomes relevant when we want to understand subgroup or subtype heterogeneity. And that is what I am referring to as tailored methods. And so for the outline, I will present one method for the one-size-fits-all using COVID-19 as an example, and I will present a method for tailored approach using COPD as an example, present to you my vision for data integration using an app that we have developed, and conclude with my thoughts on what can be done to advance data integration. So this study, this is a study that was conducted during the COVID-19, around 2021. And for this particular study, individuals who presented with COVID-19-like symptoms were admitted or not admitted to the ICU, intensive care unit at a hospital in New York. And blood samples were obtained and quantified for lipidomics, metabolomics, RNA-seq, and proteomics data. They also collected metadata, specifically clinical data and demographic data on the sex, the race, age, and some clinical information. And the key question here was to understand the complex the mechanisms of COVID-19, understand why some people go on to develop COVID-19 and why some people have severe outcomes compared to other people. So when we were trying to analyze this data, given that COVID-19 was new, and there wasn't a lot of work that has been done in that area, we thought that using nonlinear methods could help us understand the complex interaction in these molecular data. And so we looked at other approaches in the literature, but then we did find that most of the nonlinear methods, especially the deep learning methods, were not interpretable, meaning that the focus was on prediction with less regard or emphasis on the variables that drive the prediction estimate. And for this particular question, we are more interested in the variables that underlie the mechanisms of COVID-19, and we want to go beyond prediction. We also did find that some of the methods were not scalable, and some of the methods only focused on binary or categorical outcome with no emphasis on continuous outcome. And for this particular application, we had two outcomes here, COVID-19 versus not COVID-19, and we also had an outcome which was continuous, measuring how long somebody stayed in the hospital, which is hospital-free days. But then I will just focus on COVID, whether you have COVID-19 or not. And we also did find that some of the methods were not competitive in the high-dimensional setting. And so we proposed a method called RAND-MV-Learn, which stands for Randomized Multiview Learning, for jointly integrating all these different types of data whilst predicting an outcome or whilst identifying molecular signatures that discriminate between those with and without COVID-19. So the pipeline for that, I'm going to talk about how we associate or integrate these different types of data. I'm going to talk about how we achieve variable selection and how we link the association step with the integration to obtain a joint model. And so the assumption here is that each of these different types of data, so X1 represent, let's say, genomics data, X2 metabolomics, S3 proteomics, X4 lipidomics, and we can have multiple data types. So we assume that beneath there is a driving latent component, G, that drives the relationship we are observing in this data. And for this particular shared component, we believe in that space, those with COVID-19 and without COVID-19 are easily discernible. And so there is a shared component G driving all the relationship of the association that we are observing in this among the data types. And so each view can be approximated as a product of this shared component G and the loadings or the factor loadings, which we are calling B here. And in the statistical literature, we make the assumption that B is orthonormal so that we can post-multiply this X here, this approximation by BD, and then obtain G, which is approximated as the XD times B. If you look at this approximation, you can think that the BD here serves as a mapping, a linear mapping that maps each entry or each row in XD to a row in G. And this BD has been assumed to be linear in the statistical literature. So we are going to take a nonlinear approximation to BD. So we assume that the element or the rows in G, which we are calling GI, can be nonlinearly approximated as a function of the data instance. So GI is a function of our input. And so our task here is to learn this nonlinear function. We use kernels. We have other approach or techniques where we use deep neural networks, but for this particular talk, I would present our kernel approach. So we assume that this function F here lies in a reproducing kernel Hilbert space of vector valued functions. So the emphasis here is vector valued function as against scalar value function. And the reason why we choose vector value function because the dimension of this output GI is R, which is a vector. And because we're dealing with a vector value function, and so in this RKHS space, we have a kernel, which is a positive, semi-positive matrix, and it takes an input, maps it into a matrix R by R, which differentiates it from a scalar valued function. So then we can define a regularization approach to associate the different data sets by maximizing the sum of an empirical loss plus the norm in RKHS. The first term approximates the data using the shared component using the functional form, and the second term models the complexity of the data using the RKHS, the norm in the RKHS.